I love these problems. Solids of revolution, love it. It's such a wonderful application of calculus. Let's do this. Find the volume of the solid form by revolving the region bounded by the graphs of the equations about the x-axis. I do prefer those. Those are nice when it's around the x-axis. The first thing you've got to have on these is a good picture. So I'm going to sketch my graph here. If I don't know what this looks like, I'm going to graph it in my calculator. Usually on the AP test, unless it's a really easy, quadratic or linear or something, they'll actually give you the picture to go with the problem because it's that important. So you have my blessing. If you're not sure what the graph looks like, go ahead and graph it in your calculator. So e to the x over 4, well, I know what e to the x looks like, and I know that x over 4 is just probably going to change the slope, so I'm not too worried about it. So I have e to the x over 4, I have the y equals 0, or the x-axis, x equals 0, that's the y-axis, and the line x equals 6. So I can tell that this is the region that I'm going to spin around the x-axis. And then I like to draw this representative slice here. That's really going to help me later with the washer method, but it just helps me visualize, what is the radius of this disk that I'm going to add up all these areas of. Right? And so this one's pretty straightforward. The radius is just the height of the function. So I'm going to do pi times the integral from a to b. There's my a, there's the b, and that's very straightforward for us. We know that's going to be from 0 to 6. So this is pi times the integral from 0 to 6 of the radius squared. So I'm going to do e to the x over 4 squared, and I'm integrating with respect to x. That's the hardest part of these problems, is setting up that integral. Once you've set up the integral, then you're just, you're doing your thing. You know how to integrate. First thing I want to do is I want to clean up that integral to make it a little bit easier. When you have a power raised to a power, you multiply. So e to the x over 4 squared becomes e to the x over 2 dx. And I know integrating exponentials is easy if it's just e to the x, but it's not, so I've got to do a u substitution here. I've got to say u is x over 2, which makes du 1/2 dx. And if I solve for dx, that gives me 2 du. While I'm here, I'm going to go ahead and change my limits of integration. There's no reason not to do that. So when x is equal to 0, if I plug 0 in here, I just get 0. And when x is 6, I get 6 over 2. That gives me 3. So I'm going to rewrite my integral now. So I have pi times the integral from 0 to 3 now, because I changed my limits. And that's of e to the u. And then dx was equal to 2 du. So I'm going to go ahead and move that 2 out front, pull the constant out front. That's pretty easy to integrate now. So I've got 2 pi times e to the u. I'm going to evaluate that from 0 to 3. And that gives me 2 pi e to the third minus e to the 0. Anything to the 0 power is just 1. So that's all I'll do to clean this up. You can distribute the 2 pi or you can leave it factored. I would expect the book to leave that factored. Like so. Not too shabby. Let's do another one. Let's find the volume of the solid formed by revolving the region bounded by the graphs of the equations about the y-axis. Anytime you're going about the y-axis, that tells me that I'm going to need my function in terms of y. So these are fine. But when I see this one, I know at some point I'm going to have to solve that for x so that I can get my function in terms of y. Let's sketch the graph. Let's see what we're working with here. So again, that square root of 5x plus 1, if I'm not sure exactly what that looks like, I'll graph it. I have a vague idea. It's going to be square root shape like that. And then we have y equals 6 like this. And so I'm going to take this shaded region right here. Taking that region, and we're going about the y-axis. So I'm going to take my representative slice here, and I can see that that radius is just the function in terms of y. So let's go ahead and solve that. So if I have y equals square root of 5x plus 1, first I want to get the x out of the square root, so I'm going to square both sides. So y squared is 5x plus 1, and so then I can subtract the 1 over and divide by 5. So there's my function in terms of y, and that's going to be my radius that I'm going to square here for my integral. I do need to figure out what my limits of integration are, so don't forget that when you're on the y-axis, I'm looking for a to b right here. I know what b is. I know that's going to be 6. So I need to know what's that point right there. Well, that's when x is equal to 0. If I plug 0 in here, I have y is equal to the square root of 1, so that's just 1. So I know my limits of integration now are going to be from 1 to 6. Let's set that up. So I've got pi times the integral from 1 to 6 of my function in terms of y squared, integrating with respect to y. I've got to do some work here to be able to actually integrate this. I'm going to have to square that. Here's the first thing I can do. When you square something, you square the top and you square the bottom. Well, this 1 over 25, that's a constant. I can pull that out front. So I can make this pi over 25 times the integral from 1 to 6, and then I just have to worry about this piece here. I'm going to go ahead and FOIL that out. So I'll get y to the 4th minus y squared plus 1. So I FOILed that. Now that looks like something I can integrate. So I have my constant. And then when I integrate that, I get y to the 5th over 5 minus 2y to the 3rd over 3 plus y. I have to evaluate that from 1 to 6. At this point, it's just tedious. It's so tedious to plug in all these fractions. So I've already done that arithmetic, so I wouldn't waste our time here. When you plug in 6, you get 7,086 over 5. When you plug in 1, you get 8 over 15. Get a common denominator, simplify, blah, 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 blah. You get 170 pi over 3. Okay. These are tedious, I know it, and I'm sorry, but we just have to do it. So there's your disk method. We can integrate in terms of x, we can integrate in terms of y, depending on which way we're spinning around the axes.